All right, we're going to open the gates now to integration. What I mean by that is that we're going to have different kinds of integrations going on. Um, and let me first tell you what kinds of integrations we will have. In this video, we're going to have four different integrations. So we're going to have the integral over a curve of a function of two variables. You could have three variables with respect to the length of the curve. Or, so this is one bullet, one kind of integral we have to be able to figure. An integral of the same function over the same kind of curve with respect to the x variable. And then similarly, we're going to have the same kind of integral, but now with respect to the y. So those are assuming that f is a function that goes from r squared into r. That means that this is, the output is just one number. But then we can have a vector field, which we can integrate with respect to the path. Actually, it's dr, yeah, with respect to the path taken by this curve. So we have four different integrals, and we're going to see more in future videos. These are integrals over curves, and then we're going to have integrals over surfaces, and we can have integrals over solids also. So there's all kinds of integrals that now we have to be able to handle. So we're opening the gates to all different kinds of integrals of different kind of functions over different kinds of with respect to different kinds of things, such as the length or the x's or the y's. Now, in these three examples, we're assuming that f goes from r squared into r. So you have a generic region. And then we have a function. Yep. But then we take a path within that region. So the region is not as relevant as the path itself. So the path is really what we're integrating over. Yeah. And then when we do that, we're going to end up with this kind of, pretend those are vertical, those. So we're actually, I guess, a geometric interpretation of this is if the function is positive, then we're getting the area of this sheet, vertical sheet that is drawn by this path and with a variable height. I'm going to give you examples or show examples. Now, in this one, we are assuming we have a field, vector field, for instance. So this is different. And then we have a path also. And so this is a two-dimensional thing. And then we have a path, and we want to, for instance, figure out how much this field contributes to the motion along this path. All right, so let me talk more about those three again. So pretend you have, a path down here. Corresponding to this path, we have a function f. So let's say this goes up here, and then this comes up there, getting a little lower. And by the time we get down here, it gets down to nothing. So this is some kind of flag that goes down here. Yep. So the path on the floor curves, and then we have heights corresponding to the function. All right. So the first integral with respect to the length is going to give us the actual area of this sheet that S's and diminishes in height down to 0. Okay, assuming that this is the path C. So that is what the first integral does, with the integral with respect to the length. So you gotta pay close attention to the differential, because those two are gonna be very different, and potentially all of them are very, very different. So with respect to the x though, if you project the whole thing onto the x, and who knows how this is gonna curve. Yep. So if you project this, if you make a shadow of this surface, it's a vertical surface though. Usually when we talk about surfaces, we talk about not horizontal, but surfaces that are above the x and y axis. Here, this surface is a vertical surface, and then it moves around depending on the curves C. If you project that to the x z plane, you're going to end up with something like that, a flat figure. And the second integral with respect to the x-axis, or the x, is going to be, if the function is positive, equivalent to this area. So the projection of this onto the x z-axis is going to give you this area. And now you can guess what is going to happen if we do the integral with respect to the y-axis. So again, you project down here. And again, who knows how this curves? I don't know if it's going to be concave up or down. So this is just a generic curve. So if we project against the YZ plane, this wall, it's a wall that it diminishes down to nothing. If we project that onto the YZ plane, we're going to end up with another region. And this integral is going to give us the area of that region if we have a positive function. And that plus that is not equal to this. No, it would be rare when that happens. Yeah, it won't be the case that that plus that equals this. They're different things altogether. What I can say though is that each one of those two is going to be less than or equal if the function is positive to this one. This one is going to be the longest if the function is positive, or maybe equal. Yeah, something that I just thought about just now, while I'm doing this video, is whether the sum of those two exceeds this one. Yeah, if we add those two, we always get more than that. It seems that it is right, but I'm not positive. That would be good to think about. All right, so let's start with example one. Example one. So we have a curve, and it is going to be cosine of t, sine of t, as t runs between 0 and pi over 2. So this is a quarter of a circle, an x, y. And by the way, this is x and this is y. It is understood that that's the case. So we have a quarter of the unit circle. And then the function f of x, y will be 1 minus y, which is a plane. So this is the xy path. So this is c, and we had to have a direction, because if you go in the opposite direction, we're going to go negative. Whatever answer we obtain, if we reverse the direction, we're going to end up with a negative answer. All right. In 3 dimensions, this is what's going on. So this quarter of a circle will be drawn this way. And then if we go 1 unit, all right, we have a plane 1 minus y, which means we have an inclined plane that goes down this way. And then this way. So this is the plane. And so when we start here, the function is 1, the f. And then when we end here, the function goes down to 0. So we're really finding this curved area, this curved region. It's a vertical region in the sense that everything, whatever you, if you stand here and you look down on the XY plane, you will see that everything is straight. Now, this is itself curved. So it's a curved wall, and the wall keeps going down from 1 to 0. Yeah, this is the plane that we are intersecting with this. If you make this a cylinder going up, then the intersection would be this curve up here. That would be the top of this region, the vertical region. And we are finding the area of that region. Now, the only reason why I still call it area is because we have a positive function. Remember, the function goes under the XY plane, then things start going negative, and so we have an integral, not necessarily an area. So this is what's going on. The double integral, no, I meant the single integral. So this is a line integral of that function with respect to the length is defined as the integral of 1 minus y. Now remember, this is x and this is y. So when we say 1 minus y, we would have 1 minus sine of t, sine of t. So that represents f. The length, as we know, is the square root of this derivative of this guy, quantity squared, negative sine t squared. It's not going to fit here. That was not very good. So I'm going to continue underneath. So the line of the root continues plus derivative of that with respect to t, which would be cosine t quantity squared dt. And we're going to go from 0 to pi over 2, which is the quarter of a circle there. Yeah. So every time we are integrating with respect to the length, you got to take into account the length of the tangent vector. In this case, we have negative sine times cosine, and the length of that would be negative sine squared plus cosine squared, because that is the derivative of this guy. Now, if we were doing this in 3 dimensions, no problem. You have x prime squared, y prime squared, and then z prime squared. And whatever the function calls you to do, you do. So in this case, it says it calls for 1 minus y, then we do 1 minus y. If it was 1 minus x, you do 1 minus this guy. If it says 1 minus x minus y, then 1 minus this minus that. And whatever this calls for, that's what we do. If it says y squared, then just do this one squared. Or x squared, do that, and so forth. All right, this is equal to 1 no matter what. The negative, make sure when you are doing this kind of work and submitting it, make sure you put the negatives, because I check whether you have the correct derivatives in the first step, at least in the setup. Of course, when we square, the negatives are going to go away. So, but on the first place where you start putting the derivatives, make sure there's a negative. If there is a negative, if there's supposed to be a negative, here there is no negative, of course. So we end up with sine squared. The negative goes away after we square. Cosine squared added to that of the same input is going to give us 1. Square root of 1 is 1. So we're really integrating 1 minus sine of t with respect to t from 0 to pi over 2. So that is going to be, well, 1 is easy. It's just going to be t when we do the antiderivative, plug in pi over 2 and 0, so we end up with pi over 2. Minus antiderivative of sine is cosine. Well, negative cosine. So we really have another negative, so that makes this a plus. and then we're going to do cosine of t, and we're going to evaluate that from 0 to pi over 2. We're not going to evaluate that, only this. So when we put in this line for evaluating and subtracting, that refers to whatever function is next to that vertical line. If I wanted that to be evaluated too, then we go and put a parenthesis. So that is an important notation we have to keep in mind. So let me double check. Derivative of cosine is negative sine. Yep, that works. And so this is pi over 2 plus cosine of pi over 2, which is 0 minus cosine of 0 is 1. So we really end up with pi over 2, which is about 1.57 minus 1. So that is about 0.57. Yep. So this is the final answer. Please box the exact answer. Don't box the decimal unless I ask for a decimal. Don't write a decimal, please. So, but I just want to have an idea of how much that is. So 0.57 units. So as this curves around, we're going to end up with 0.57 units. Yep. And those I guess would be square units. So that is example 1. Example 2. Same curve, same function. So f of x, y will be 1 minus y. The curve C is defined by r of t. Did I put that on the previous? I think my notation is incorrect here. Let's fix it before we move on. C is defined by r of t equals this, and that's what how C is represented. So it isn't that C is equal to that. That was bad notation. This is not an exponent. This is r of t equals that. So R defines the curve C. All right, so again, r of t will be cosine t sine t close parenthesis. And then we have to specify from where to where, because if you just let it run around or let t run free, then you can just draw a whole circle multiple times. So we just have to specify from where to where. And that tells us we're going to go a quarter of a circle. All right. So the integral of f with respect to x on the curve is going to be defined as, and that's something I didn't do in the last example, I didn't define it. What the integral is, we're going to define it probably after we finish this guy. So here we define this as the integral of f of x of t, y of t, indicating that we're going to plug in those two. And then derivative of x with respect to t dt, that indicates that we're doing with respect to x. So we're multiplying with segments of x from a to b, whatever. So this is a generic formula from a to b, and this is the general formula. Of course, you wouldn't put a, so this is the general formula. We wouldn't put a and b if you already know what to put in here. So this is just the definition, the general definition of the integral with respect to x, or I take that back. It's not the definition. It is just the way we find it. The definition would be, well, multiply segments of x by heights of f as a Riemann sum, and then take the limit as those guys get smaller and smaller. Anyway, let's figure this out. So what we are looking for in our particular case will be the function, which is 1 minus y, but this is y. So the integral of 1 minus sine of t, derivative of x with respect to t. This is x, remember, cosine of t. So the derivative is negative sine dt, and we go from 0 to pi over 2. Okay, so, interesting. There is a next, I'm just double checking, yep. Well, let's go for this. We're gonna end up with the integral from 0 to pi over 2 of negative sine of t plus sine squared of t dt. So the integral of sine of t from 0 to pi over 2, the antiderivative is going to be cosine of t, all right, from 0 to pi over 2. Let's split that into two integrals. This one is fairly straightforward. Derivative of cosine is negative sine, so there it is. Plus, and here we need to do this trick of changing sine squared into 1 minus cosine of 2t over 2 dt, still from 0 to pi over 2. And then we'll handle that well in the next step. So cosine of pi over 2, again, is 0 minus 1. That takes care of this portion of the problem, plus, or the solution rather. Here we have 1/2, but then we're just plain 1/2, the constant 1/2, as we go from 0 to pi over 2. Of course, we just multiply by pi over 2, and that takes care of this, this 1/2. Now cosine, the antiderivative of cosine is sine, so we have sine of 2t from 0 to pi over 2. And if you notice, we have to divide by 2 because this 2 also divides the cosine, so that carries over. In addition to that 2, we have another 2 because of this extra 2. So if you use substitution, u equals 2t, du equals 2 dt. So we have an extra 2 to take care of, and we have to divide by another 2. So there's a 2 coming here, another 2 coming from another, people would call it chain rule backwards. And so we have a 4 in there. So we have negative 1 plus pi over 4 minus, all right. Oh, this is interesting. When we plug in pi over 2 here into t, we're going to get just pi. Sine of pi is 0, and then that's 0 as well. Yes, so this is going to give us minus 0 plus 0. So the final answer is pi over 4 minus 1. I'm going to box it. Pi over 4 minus 1. I'm looking for a solution, perhaps. I want to have an idea of how much this is in a calculator, a decimal. Box the exact answer, don't box the decimal, please. That's just so I have an idea of how much it is. So here we have 3.14 minus 1. Oh no, let's divide by 4 first. Divide by 4. This is an approximation, of course, that's about that. Subtract 1, and we get about 2.150, and it is negative 0.215. So the first question we should ask ourselves is, wait a minute, this is a negative number. Isn't it supposed to be an area? And In this case, yes and no. All right, let's draw the, so this is the bottom. It comes up here and then it goes down to this. And we're multiplying heights times lengths. Oh, no. That was the example one. Our example two is with respect to x. So new picture. Okay, so we go down this way there. So we are looking at the graph of this thing on the, not on the, on this curve, the projection of this curve, this surface rather, onto the xz plane, and we're looking at it, the projection, and finding the integral of that region. Okay, so there's the xz plane. I'm not going to put the y, and we're going to end up with something that perhaps looks like this. I don't know if this curves, if this is concave up or concave down. We don't know because we will have to do more analysis of this. But here we have that. So that is the projection of this onto the xz plane, projecting. All right. Now, this curve is being drawn starting here this way, which means that the projection is being drawn from this point inward towards the origin. So this is the direction. Now, let's think about it. We're multiplying delta x's with a function. But the delta, when we go, and this is the positive x-axis, because that is this line here. Okay, so when we go in the opposite direction as the x-axis increases, the delta x is corresponding to, before we take the limit, to the integral before we take the limit, are going to be negative. That explains why we end up with a negative answer, because the way the curve is going from positive x-axis towards the negative of the x-axis. Consequently, the delta x's corresponding to the integral, before we integrate, all of them are going to be negative. All of them are negative. And that's why we're multiplying negative delta x's. So let me draw, sorry to keep doing this here. So this is what's going on. This is the x-axis, positive x-axis, the z-axis. So we are really, before we do limits, we're multiplying basis times height, just as we did in Calc 1 or even Calc 2. The difference here is that because this is the positive axis and we're going in that direction, all the delta x's are going to be negative. And that explains why we have this. So if you really wanted to find the area of the projection, taking that into account, that the delta x's are going to be negative, just multiply by -1, and we end up with about 0.21 or 22 square units. Yeah. So, yeah. So you got to be very, very careful. Now, example 3 will be the integral with respect to y, and we're going to do example 3. But something I want to say before we start example 3 is that in example 1, when we did the integral with respect to the length, we got about 0.57. The magnitude of this, or the absolute value of this, would be 0.22. It would be naive to think that, oh, the other answer will be 0.57 minus 0.22, 0.34 or whatever. No, that is not the case. So let's do example 3. Example 3. So C, the curve, is defined by R of t, which is going to be same circle, except that we're going to go from 0 to pi over 2. So it's really a quarter of a circle. The function is still going to be the same so that we can compare with our previous examples. And so, yeah, the integral of f with respect to y on the curve is going to be similar to this. I don't think I need to rewrite that. You can find this in any book, except that we're going to multiply with dy dt. So the function dy dt dt. Okay. So the function is going to be 1 minus y. There is x, there is y. So 1 minus sine of t as before. Derivative of y with respect to t, because we are doing this integral with respect to y. So y with respect to t is going to be cosine of t dt from 0 to pi over 2 on the t's, from 0 to pi over 2. So we have the integral from 0 to pi over 2. When we distribute, cosine of t minus sine t cosine t, close parenthesis, dt. Antiderivative of cosine is sine, sine of t from 0 to pi over 2. Now here we can set substitution. If u is equal to sine of t, du is going to be cosine of t dt. So we're really integrating u, the sine, because this makes up the du. When t is 0, we have 0. When t is pi over 2, we end up with 1. Sine of pi over 2 is 1 minus 0 minus, this is going to be u squared over 2, plug in 1, half, plug in 0, you still get half. Or you still get 0, rather. So 1 minus a half is a half. There we go. So there is the final answer for example 3, which is, oh, it's not an approximation. It is exactly 0.5. Yep. So there is a curve going this way. If we project the curve onto the z plane, we're going to have something like this. So we just found that this area is 0.5. And we don't know whether this is straight or curved. I wouldn't dare to say one way or the other. The fact that we got a half kind of would suggest that it is straight, but I don't know. We would have to do further analysis to figure that out. And then we have another, this, I'm guessing it's going to be concave up, another area here. Okay, so the area there is the absolute value of pi over 4 minus 1. That's example 2 from example 2. The area of this, by the way, just putting an absolute value doesn't guarantee that we get the area. I know that it is the case because of the way this moves to the right from our view. This moves towards the origin from the positive x-axis, and it doesn't come back. If this curve was s-ing, going forward and then back and forward, then the absolute value does not give us the area of the projection anymore, because we would have some negative and some positive and negatives that don't necessarily add up correctly. Since this is uniform going towards the origin, I know the absolute value will be the area. Remember, this number was negative. How much was it? About 0.20. I'm going to round it to negative 0.20. Well, with the absolute value that is about 0.22. We just found out that this area is 0.5 exactly. And we knew that this one, this area here is 0. That was example 1, about 0.57. So about 0.57. So something I wanted to show you is adding this with that is not going to give us this one because it's curving and the projection is not the same as the area of the object that is being projected. So no, so those are the three things that we could do with a curve and a integration, a function f, and an integration with respect to the length, with respect to the x, and with respect to the y. Yes. Yeah. Oh, there's one other thing we need to do. Example 4. Yes, or that I wanted to do. So let's take a path. Yeah. So evaluate the integral CF with respect to, let's say, the length. Good. Yeah. Where C is the straight path from the point, let me draw a quick picture so I know. So this point to this point down here. So from 0, 1 to 1, 0. C is the straight path from the point 0, 1 to 1, 0. So those are all the instructions. Oh, f of x, y is still 1 minus y. So we're still on the same plane. Okay. I just thought we can do this geometrically now that I think about it. Yeah, if things are just right, we can do some problems geometrically. So the path goes from from 0, 1, which would be here, to this point, so this direction. It is important to know the direction because otherwise you're going to end up with the opposite. And then the inclined plane goes from 1 to 0. Yep. And again from 1 to 0. Oh, I don't know if I can do this geometrically anymore. I thought, yeah, I might be able to, but I wasn't planning on. So really, we have, maybe we could. So this is the height. So when we go from here to here, and the function goes down as we go away from the x-axis or the xz plane, what we have is this triangle, because this is a plane and this is a straight line. I'm pretty sure that this is going to be a straight line as well when we intersect. So this is the triangle for which we're finding the integral with respect to the length. If the function is positive and we are integrating with respect to the length, the answer will always be positive. So the direction that we're taking shouldn't matter because the length has a square root and the square root makes that positive. So the only way we can get a negative solution for an integral is if the function itself is negative. But between, which could be if y is bigger than 1. But in this case, y is never bigger than 1. All right. Yeah, we can find this area. That's geometrically. We shouldn't do it geometrically for purposes of this section, but now I'm curious. So this is the base of a right triangle, which has a length of square root of 2. So the length of this guy is square root of 2 because we got 1 and 1, 2, and then the square root by Pythagoras, that's square root of 2. The height is 1. So 1 times square root of 2 is square root of 2, divided by 2 is square root of 2 over 2. So I'm pretty sure the answer is going to be square root of 2 over 2. But let's do this. So let me geometrically. The answer is, so the base is square root of 2 times the height divided by 2 because we got a triangle and those are the base. And then when we simplify, we get 1 over the square root of 2. But let's see. It is very important to know how to parameterize a segment. So this example is very, very important because we need to know how to parameterize a segment. See, in the previous examples, the curve was already given to us. It's a quarter of a circle, so we know what to put for x and y. Here, they're not telling us the equation of the curve. So we have to come up with that ourselves. All right, so the curve is given by r of t. So we're gonna have, okay, so we're gonna start with this, the vector 1, 0, and we're gonna start with a whole of it. So 1 minus t. As t increases, okay, then 1 minus t decreases. Let's assume, by the way, that t is gonna go from 0 to 1. That makes a nice integration. The reason why we're picking this, among other reasons, is because it makes a nice, easy integration, easier than if we were using different numbers. Excuse me. Excuse me. So 1 minus t works really well to start with 1, 0. Wait, I'm looking at my picture differently. I want to start here and end there. Yeah, so I want to start with 0, 1. Let me try to erase this very quickly. So the vector I want to start with is not there. We don't want to start with 1, 0. We want to start with 0, 1. 0, 1. When t is 0, we have all of this, a 1 of it. And when t is 0, we have nothing of the one we want to end up with. We want to end up with 1, 0. 1, 0. So that's how we put this equation together. Nothing of 1, 0, all of 0, 1. As t goes to 1, 1 minus 1 is going to be 0. So we have nothing of this and all of that. So we are little by little starting with 100% of this, 0% of that. When t gets to be 0.01, for instance, as it runs from 0 to 1, we get 99% and 1% of that, 98% and 2%, 97%, 3%. And little by little, we keep adding more of this vector and less of that vector, thus traveling on this segment of line. Now we gotta simplify this into one vector. So we have 1 minus t on the second coordinate and t on the first coordinate. So this is equal, let me just write it down. R of t equals 1 minus t on the second coordinate, 1 minus t on the second coordinate, and t on the first coordinate. There we go. And again, t goes from 0 to 1. So when t is 0, we get 0, 1 as we wanted it. When t is 1, we get 1, 0. Yep, so we go down this way. Okay. I did not write the general rule for this, how we find this. So let me write this down. General rule for the integral f on a curve with respect to the length. And that is, I'm going to write it underneath. The integral from a to b, assuming that we start in a and b, a generic a and b, f of x of t, y of t, times derivative of x with respect to t squared time plus derivative of y with respect to t squared dt. dt. Okay, so that is the general rule how we do this. Now, I want to emphasize, many times we don't give you this equation. If it's a straight path especially, you have to come up with that. And I just explained how. So example 4 still. We are continuing with example 4. R of t is, from the previous page, t, comma, 1 minus t. And f, well, as t goes from 0 to 1, f of x, y equals 1 minus y. I'm just putting pages on my sheets. All right, so the integral, the line integral of this function with respect to the path, no, with respect to the length, sorry, is integral 1 minus y. Now, mind, this is y. So 1 minus y, this is x and that is y. So we do y, quantity 1 minus t. Okay, so that is 1 minus y, 1 minus y. Derivative of this with respect to t is 1, square root of 1 squared. Derivative of that with respect to t plus negative 1 squared dt from 0 to 1. All right, so negative, those two subtract, double negative means t, 1 squared plus 1 squared is 2, square root of 2. So we are integrating t from 0 to 1, t square root of 2 dt. Of course, that is going to be t squared over 2, plug in 1 and 0. So square root of 2, that square root of 2, but then t squared over 2, which is 1 over the square root of 2, as we anticipated. Yep. So we have established earlier by geometry that we were going to end up with 1 over the square root of 2. Now, this is an easy problem. Many times things are not going to be that easy. They're going to be more like example 1, where we have a curve. And then once you take into account the curve, then we don't know what's going on anymore. We cannot say one or another thing is going to happen until we have evidence of what we're saying or what we be saying. Example 5, a very useful example. Okay, so the path is made up in example 5. It's going to be made up in 2 parts. I'm going to describe it to you. So we're going to go quarter of a unit circle and then come back in a straight line, straight back to where we started. So let me draw a picture again. Quarter of a unit circle and straight back. So it's going to be a loop, except that usually loops are nice and smooth. This loop sharply turns around, not exactly 180 degrees. 45 degrees, because the tangent here would be horizontal of the circle. So about exactly 45 degrees. So as a sharp turn, or the other way around, 360 minus 45 degrees, so 315 degrees, turn all the way around, start going straight. So this is what's going on. We go out this way and then make a 315 degrees and then start coming back straight. So that's what this motion indicates. Go and then come back. So see as described below. So this is a unit, and I'm telling you it's a unit circle, so quarter of a circle and then come back sharply. We have to know f. F is equal to 1 minus y, so same as before. And the question is, what is the integral on this path of this function with respect to the length? So oftentimes we're going to have a path that is not defined by one curve. This is defined by two curves. Oftentimes you're going to have a square, so up, across, down, horizontally. We should do one of those. At least, no, actually, example 4 does that. If you have a square and you go up, across, down, and then come back to the same, we would be doing 4 of these problems where you have to find these segments one by one. So we don't necessarily have to do that. Anyway, but the thing I wanted to say is that the curve could be made up by multiple curves. And sometimes we come back to the same spot where we started. In this case, we don't end up with 0. Some people may say, well, you're going and then coming back, so shouldn't you end up with 0? And the answer is no, we don't. We can split this up into two paths. The paths, oftentimes we label them as C1 and then C2 in order in which they are being drawn. Starting here, we go up and then come back. So C1 and C2. So this is the same thing as the integral over C1 of f ds plus the integral over C2, same thing. But this is example 1. And this guy is example 4, the one we just finished. So there's no need to redo that. Example 1. Gave us pi over 2 minus 1. An example 2. Now, mind, this is a negative number. That's fine. Leave it. That's okay. An example 2 is going to be, rather, example 4, the answer to that is still here on the same page, 1 over the square root of 2. So there, that is the answer. Go and come back. The line integral. Oftentimes when we go and come back to the same spot, we put a circle on the integral, indicating that we are going back to the same spot where we started on the path. But notice that we don't get 0. This is a negative number, this is a positive number, but there's no way those two are equal. No, they're not. So no. Yeah, we cannot, these are, yeah, this is not going to be a 0. You can punch it into your calculator and you will realize that this is not 0. So this is example 5, and that covers these 3 cases where we have an integral of a function of several variables with respect to the length, with respect to x, and with respect to y. We only did one example of those. We could do examples, but that is going to be we can figure this out geometrically with respect to the x-axis and with respect to the y-axis, but I'll let you work those out. And we're going to move on to vector fields and line integrals on vector fields. So if we have f, on a curve, the way we define this, now this is a capital F indicating that we have a vector field. So this is going to be a vector. The output of this is a vector. And this is going to be the dot product. Dot product. So the way we do this is by integrating the dot product of f, which is, remember, a vector, with r prime, another vector, the dot product, dt. So we're going to turn that into a regular integral from a to b, which are the t values that correspond to the starting and the end of the path. Okay, so let's do a few examples. Okay, so these examples are going to be simple because we want to understand what this means. This has to do with work. If the path, no, if the force, pretend that we have a force field. If the force contributes to the motion, then we have more work. If the path, no, if the force field does not contribute to the motion, then we have less work. And that's why the dot product is important, because the dot product measures when things are going in the same direction versus things that are perpendicular. The dot product of 90 degrees is 0. And so when the force does not contribute whatsoever to the motion, then we have no work done. So the word work, in my personal opinion, is misleading, because what it measures in physics is how much the force contributes to the path, not necessarily how much energy it is being used. But that's just me. That is my personal point of view only. See, and it's good that I don't say more than that, because I know math, some math, but I do not know too much about physics. So, example 6. This few examples, we're going to do a few examples that are very, very straightforward to help us understand what this is about. So the force, or the vector field, is going to be a constant. It is going to be 0, 3. The path we're going to take, r of t, is going to be a straight line. It is going to go 5t, 7, as t runs from 0 to 2. 0 less than or equal to t less than or equal to 2. So we got vector field. So these are lines going up, or vectors going up. So f is just lines going up. Those are supposed to be vertical. The path we're going to take starts with 0, 7. So somewhere in here, 0, 7. And it's going to be 7 no matter what. And we're going to end at 10, 7. So from 0, 7 to 10, 7. 0, 7 to 10, 7. And we want to know the contribution of this. So we have pretend this is physics and this is a particle that is moving. We have a motion going horizontally in spite of a vector field that is going perpendicular. What we know about work implies that there's no contribution of this vector field to the motion, so the dot product of those two should be 0. Well, let's apply this. Now this is constant. All of those vectors going up are the same length. So the line integral of that with respect to the path is equal to, of the vector field, is equal to the integral. So we're converting a line integral into an integral, a regular integral, where we are going to do the dot product of 0, 3, 0, 3, with dot product with 5t, 5t, comma, oh, no, the derivative. So just 5, comma, 0 dt as t goes from 0 to 2. So the dot product is 0 times 5 is 0 plus 3 times 0 is 0. So right there, even before we do the integral, we are just integrating 0, which of course is going to give us 0 no matter what. So that is just 0, as anticipated. This is not the vector 0, this is just the number 0, which means there's no work done here. Now, as I mentioned earlier, that doesn't mean there's no energy being used as we go from here to here. What it means is that this force, if we think of this as force, did not contribute at all to the motion. Okay, let's do example 7. The force is going to be 3, 0. So now we go horizontally. So we have a vector field going horizontally. The motion is going to happen from 0, 7 still. So the path is still going to be 5t 7, 0 less than or equal to t less than or equal to 2. So we're changing this dramatically in the sense that we're going 90 degrees. The force is going 90 degrees now. So we go in the same path as here from 0, 7 to 10, 7 in that direction. So now the force contributes completely to the motion. How much? In a way, this measures, in my opinion, again, efficiency. How efficient is this force as far as helping this move? But that's me again. So the line integral of the vector field with respect to the path that we are taking will be so 3, 0 dotted with the derivative of the path, which is 5, 0. Sure enough, with respect to t from 0 to 2. So that's going to give us 5 times 3, 15 integral, so equals 15 with respect to t from 0 to 2. And of course, that is going to give us 15t, plug in the 2, plug in the 0, and that's going to give us 30. Yeah, 30. I don't know what the units will be. This is if this is a distance, let's say meters, and the force is in newtons, then you would know what this is. All right, but something I want to ask myself is, what is the answer if we take this path not as quickly? So this path, assume t's time, goes from 0, 7 to 10, 7. So 10, pretend we have meters, 10 meters in 2 seconds. That is very, very fast. What if we take exactly the same path at a lower rate? Exactly the same path. Is this number going to be different, or is it going to be the same? That's going to be example 8. I'm just looking through my pages. So page 7. All right. Example 8. So the vector field will be the same, 3, 0. The path, we're going to change it. Instead of 5t, let's just make it t, 7. Same path, but now it is going to take way longer, from 0 to 10. So it's going to take 10 seconds, as opposed to in example 7, 2 seconds to get to the same thing. So same picture, same force field, if you will. We're going to take a path starting at 0, 7, ending at 10, 7 in that direction. Okay. What is the line integral? So the line integral of this with respect to r is going to be 3, 0. The integral of the dot product of 3, 0 with the derivative of this 1, 7, no, 1, 0 rather, with respect to t from 0 to 10. Oh, I can already see what's going on. We're going to end up with 3 times 1, 3 from 0 to 10 dt. And of course, that is going to be 30. That's important to know. So how fast the line is being drawn, as long as we start and end on the same spot, seems to be irrelevant to the work. If we think of this as the work, or the line integral of the force times the, or dotted with the path. Yeah, that is very, very interesting, I think. Let's do an example that is not so simple. Let's say we have a force field. Let's see, x squared square root of y. And then the path is given by r of t equals cosine of t, sine of t. And again, as t goes from 0 to pi over 2. So this, let's just draw a few of those vectors. So for instance, when we are at 1, 1, the direction is 1, 1. 1, 0, we have this vector. 0, 1 is going to be this vector here. And probably this is going to fan out, but not necessarily the same as the radius of a circle. It's going to fan out differently. The slopes are not proportional to where we are, the angle in which we are. So for instance, yeah, 2, if x is 2 and y is 1, so we end up with 4, 1. Yeah, this is, so here we're going to be at 4, 1, which is a very steep slope. So, but then if we are at 0, 2, or rather 1, 2, then we're going to be if the x is 1 and 2, then we're going to end up with 1 square root of 2, which is not as steep as that, but it's still going to be going up. So here we're going to be, yeah, perhaps something like this. Yeah, so it is kind of weird. It seems that the vectors are going on the upper right direction, but they're not necessarily a nice uniform kind of vectors. So this is some field that I just made up. And the question is, as we go in this path, what is the integral over that path of this vector field? All right, so the integral, the path integral with respect to r will be, let's see, the dot product of x squared. Now, x squared is really cosine squared. Yeah, cosine squared of t, comma, square root of y. So that means square root of the sine of t dot it with, I'm running out of space here, so I'm going to continue on the next line, the derivative of the path. So that is going to be negative sine t, comma, cosine t, dt, and the integral goes from 0 to pi over 2. Okay, so that product gives us negative cosine squared, cosine squared t sine t plus the product of those two, square root of sine t cosine t, close parenthesis, dt from 0 to pi over 2. I think we can do this on the rest of the page. Here we're going to use substitution, of course. If cosine, split this into two integrals, and in each one of those, we're going to use substitution. If u is cosine of t, then we will have u squared, and this, the negative sign actually works really well. We're going to end up with du, negative sine dt mix up the du, because the derivative of cosine is negative sine, and we already have it. Here we're going to do a different kind of substitution, so I'm going to use a different variable. Say v is going to be sine of t, dv is going to be cosine of t dt, cosine of t dt. So that will work really, really nicely. So we're going to end up with the integral of u squared du. Now let's be careful. When t is 0, we get 1. So we're going to go from 1 to 0 because the cosine of pi over 2 is 0. Plus the integral of u to the 1/2. And this one is going to work out nicely from 0 to 1. Oh, this is a v, dv. V, okay. So that is going to be u cubed over 3. Again, u cubed over 3. So we're going to end up with 0 cubed over 3 minus 1 cubed over 3. Plus, maybe I won't be able to finish this on this page. So this is v to the 3/2 over 3/2, so 2/3 of, oh, I guess maybe we'll see. So 2/3 minus 1/3. Well, at the end, the final answer is 1/3. 1/3. Yep. So the contribution of all those vectors on the path going around, it is a quarter of a circle on this path or this motion will be 1/3. Yep. Make sure you practice this line integrations. Line integrations are plentiful. They happen a lot in multivariable calculus. And with this, we will stop the video.